Okay. So it says examine a piece of magnesium ribbon. Using crucible tongs, ignite the magnesium in the flame. So when we hear flame, I know most of us are like combustion, but that's not what we're looking at. Of course, the fire has to combust. That's how fire works. You light a fuel with oxygen. So the fire is just going whatsoever. That's not the reaction we're looking at. We're looking at magnesium. Well, then magnesium went from this silvery thing to this white brittle substance that was on the end of the crucible tongs. What do you think happened to straight up Mg? Mg, can it decompose? Yay or nay? No, magnesium is a pure element. It cannot decompose. So then you're like, okay, well, maybe it combusted, maybe it reacted with oxygen. Well, oxygen definitely is a gas that's present. So it's going to be an oxygen species that's going to react with it. So O2 is what some people forgot, the diatomic part of that. And so when you combine it, yes, you can call it combustion, but combustion was not an option on this lab. It said synthesis, decomp, single, and decomposition. So you couldn't commit to combustion. You had to commit to something else. What would this type of reaction be? Synthesis, right. So then what does this synthesize to make? MgO, because it's Mg2 plus, oxygen 2 minus, crisscross. And I saw a lot of people put Mg2O2, which disappointed me, because you know you have to reduce to the empirical formula. And that's 1 and 1. So what's the name of MgO? Magnesium oxide. You're like, this language I've forgotten. Magnesium oxide. Okay. So then you see the 2 here. So what do you have to do over here? Put a 2, and then you have to also put a 2 over here. Okay. So some of us got that one, but that one is definitely synthesis in this case, because you take 2 elements, bring it down into 1 compound. Next one, we have this copper 2 sulfate. What is the formula for copper 2 sulfate? Shout it out. CuSO4. Anything? No. Copper 2, sulfate has a 2 charge, crisscross down to 1. You can even put a parentheses around sulfate if you want to keep it a happy family. It's a polyatomic ion. So this is going to be combined with iron filings, which is just iron solid. That's Fe. And so what kind of, looking at this, what kind of reaction is it? So we're all saying single, but how do you know that? Just by looking at it. Maddie. Well, there's 3 things, yeah, but so what are you saying has to happen? Okay, so there's 1 replacement, a single replacement. The iron and the copper just are singly replacing each other. And the reason you know that is because what? You guys have a little sheet in front of you? Who's more attractive? Look on here. You don't have to know it. You have to be able to read it. Iron. So iron is the free one. Iron is the single guy or gal. Iron has to be more attractive than copper, because copper is combined in this relationship. Iron wants to get in there. So iron's higher than copper. Copper's really surprisingly quite low in the activity series. So yes, iron does replace. And I said iron's most common charge is 3+, like copper's most common charge is 2+. So iron is going to have a 3+ charge when it combines. And I didn't take off on some people's because I made it work for you, but other people, your charge just didn't crisscross. So tell me what it would make. Fe. I hear FeSO4, I hear that, but tell me some charges. 2 from the sulfate and 3 from the iron, and Cu. Do not put a 2 there. It's not diatomic. Diatomic species are only the big 7 and hydrogen, none of the metals. And so that 2 is just in your head because you know copper has a 2 charge, but not here. It's a solid copper, whereas this is like a copper ion. Those are 2 different things. So then to balance it, you would need a 3 here, 2 here, 3 here. Okay? So what happened in this one? This was a pretty blue color, okay? Beautiful blue color. This was like a black kind of particulated metal. What happened? What did it look like after the reaction? What color did the black particulate stuff turn? Reddish orange. Well, it's not that turning a color. It's not iron anymore. It's actually copper because it's singly replaced. So there is no free iron anymore whatsoever unless something didn't 100% react. But all that reddish copper colored stuff is just copper. That's it. So then all that blue color should have disappeared. Some made like a kind of a green or a clear color. And that's just the iron 3 sulfate that's floating around, which doesn't have a pretty blue color like the copper does. This is kind of clear-ish, kind of green, yeah, clearish, and this was just copper in color, kind of red in color. So don't think that it's just the iron changing color. It's literally a new compound. That's what chemical reactions are. They make new compounds. Okay, next. Barium chloride formula. Barium chloride. BaCl2. That 2 comes from barium's charge. Good. And sodium carbonate. Good. Na2. Where's that 2 coming from? Carbonate's charge. Good. So this is CO3, 2 minus, the 2 minus scooches down there. This is a double replacement because there's 2 things that can switch. And so in this case, barium gets up with who? Carbonate, right? This barium, which is a plus charge, and the carbonate get together to make barium carbonate. What's the formula? CO3, right? So where the barium's got a 2 charge, carbonate's got a 2 charge, crisscross, they reduce down to 1 and 1. And what else gets together? Right, the Na plus and the Cl minus, and so that has to be crisscrossed just to make NaCl, because they're both 1s and 1s. But in this case, we need a balance now, so what do I need to do? 2 in front of the sodium chloride, right? Okay, so now here's where we, in the single replacement stuff, we use the activity series. In the double replacement, what do we look at? What tool? Solubility rules. So tell me, who's the insoluble product here? Niall. With me? Tell me who's the insoluble product of this particular reaction. So what's the name of that? Barium. There's no chlor, because that's chlorine. You're thinking chlorine. Carbonate, barium carbonate. So you put a little precipitation there. Everything else would be aqueous, right? This is the part where this was not asked on this lab, but let's go for it anyway. Let's write the NIE for this. Okay, so the net ionic equation. Remind me how we do that. I'm going to kind of scooch it down here. Okay, so you should be writing this because I know nobody's done this yet. Okay, so when you write the NIE, the net ionic equation, what's the ionic part referring to? What do you do with the soluble ionic ones? Right, you ionize them. You break them back into their individual components. So this is aqueous, this is aqueous, this is a precipitate. Don't touch this, right? Leave it alone, box it off if you need to. This is aqueous. So the aqueous ones are ionizable. So we're going to break them up. So what does the barium chloride become? Ba2 plus and Cl charge 1 minus. And how many chlorines are there? 2 of them. That 2 subscript does say there are 2 chlorines, even a 2 right here in the front. All right, let me call on somebody and get some else here. Allison, tell me what the next one of the ions for the next one would be. Na plus, and how many are there of them? 2, because that 2 says there's 2 there. Evan, what's the other one in this one? Right, so carbonate is its own single atom, or ion, and so that's going to all kind of break apart, and then we're going to yield to the barium carbonate, which does not break apart. Keep it in its solid kind of combined form. Scott, tell me one of the other ones. Another ions that are made in this product part. How many? This 2, yeah, that 2 actually is going to distribute both times, right? There's 2 sodium ions and what else? So 2 chlorine, so 2 Cl minuses. Don't forget the charges on these, because that's why they're called ions, right? Okay, Brandon, who are the spectator ions? Who are the ones that are just chilling and watching and not playing in this game? Right, so the 2 chlorides are exactly the same. They're spectators. They're still there. They're just not represented in the action plan here. And then the sodium ions are still there. They're just not playing in the game. So the full NIE would be what? Avery, tell me the full NIE, just the after we cancel. Precipitate. Good. Awesome. So the NIE part requires us to look at solubility rules and cancel spectators. Yeah.
Now for NIE, do we have to write the charges?
Whenever yeah, right here and here.
Even if they are could cancel.
Yeah, because they cancel here, but we're showing the process. We're showing them as individual ions, and then they come together to make the compound. So that's why it's called the net ionic, because you do write the charges. Yeah. Niall told me, first of all, but I just believed him. So whenever you look at the solubility rules, you look at the insoluble products, which is the bottom one, and it says carbonates. Carbonates are insoluble, so all the carbonates are going to be precipitating, unless it's the exception, but the exceptions are like alkali, metal, and ammonium, and that's not one of the exceptions, so we continue to think of it as an insoluble product. So you get to use this. That's why. Yes, that's why it does dissolve with the chloride here, and the carbonate dissolves with the sodium because it's an alkali metal. Yeah, good point. Okay. All right, so NIEs, we're kind of refreshing there. We'll keep working on those. The last one was sodium bicarbonate, right? Sodium bicarbonate. What's the formula for sodium bicarbonate? NaHCO3, right. And this is one we actually went over in terms of the product, and most of it's got this because I actually did it for you. But the flame test is that little stick that you light on fire, and you're supposed to blow it out. Or you can have it like a really tiny low flame. And you insert it where gas is being produced, and it's an indicator for the type of gas produced. If the flame goes out, what kind of gas is being produced? Carbon dioxide. And we know that you guys are like, it keeps going out. They're like, something's wrong. I'm like, just make your observations. It's CO2 that was being produced. What if it had flared up and gotten bigger? What gas do you think would have made the flame get bigger? Oxygen. So I'm going to try to show you guys that today. I have a demo for you. And then there's another one that's kind of weird, and I've tried to make it work, but it doesn't always work all the time, so I'll try it again. But it goes like, it has a bark to it. It's called the hydrogen bark. So if it makes hydrogen gas, it goes, it makes like a bark sound. So I will not do the bark sound again. But there you go. Okay, so it sounds like a dog. That's why it's called a hydrogen bark test. Okay, so this one made water, which you saw on the side of the test tube, the carbon dioxide, which you were noticing from the flame test, and then sodium, what? Sodium oxide, which is what's the formula? 2. Oh, because the oxygen has to crisscross the 2 down. And I think you just put the 2 over here. Okay, the last question that was really bothering me when I was grading these was, actually, I think you guys are okay on this one, but number 1, evidences. Some of you guys said it combusted, or it, I think most of the one that was wrong is that it's combusted. So what are some evidences that a chemical reaction is taking place? First of all, you saw an unexpected color change from the metallic silvery color to the white powder, right? And that's like, oh, I didn't think it would do that. Another one is that light was made, light production. You saw it got really, really bright, right? So that's not really on fire. It was kind of on fire, but it's just really bright. So light production, there's also probably heat production with that. So those would be 3 really acceptable ones. Combustion is like a totally new chemical reaction. And you could say fire made, but maybe not the term combustion, because that would be like the type of reaction, not really your observation. Okay, do we feel like we remember some of that? Yeah? Okay. Let's look at, we'll try these real fast. So I want to make sure we have time at the end of class for our Mythbusters. So before we move on, this is yours to write on. This is yours. Keep it. Go ahead and work with somebody next to you on the types of reactions. Maybe let's go 5 or 10 minutes, because this is your homework. I want you to get start on just the types of reactions right now, okay? Just the types of reactions right now. Wait, okay. So start on the balanced chemical equations part where you have to predict the products.
I don't know.
Do the types and then predict the products and balance.
I want to say it's second, fourth. I don't know what to do. So.
Thank you. This concert was so much fun to go to. It was in Greensboro. No, it wasn't. This was like a few years ago. You have one coming in May. Maybe so. What? Oh.
Yeah, that was.
I'm not so sure for you.
Yeah.
You think it's a good idea?
All right, you can keep working, but I want to make sure we're good with the types, and then you have to predict the products. Matt, what kind of number is the first one right here? Single replacement. Is magnesium more active?
Yes.
Yes, copper's really low. Sorry, I got caught with chocolate crown. So magnesium will replace that, will replace, and go on. Avery, what kind of reaction is number 70? Right, it's a double displacement or double replacement, however you want to say it. So we'll use the solubility rules there. Trinity, what kind of reaction is the next one? Yes, anyone. Combustion is a good one because you can say it's reactive oxidation, or you can call it synthesis. And on the paper it says like composition. For the synthesis one, there's sometimes multiple names, and that will come together to make what? It's got to come to a compound that you know and you're aware of because you have to crisscross the charges, right? So that's going to make H2O because H is a 1 plus, O has a 2 minus, crisscross to water, makes water. What kind is number 73, Niall? Right, it's one thing. It's can only do one thing. It can break down. That's it. What about 76? Evan, what kind is number 76? So close, but look at the presence of oxygen. What does that scream to you? Combustion. And this is a special combustion. This is combustion of a hydrocarbon. Think about what C3H8 is. Think about it. Anybody got me? This is that organic nomenclature. What's C3? What's 3 carbons called? Pro, right? Pro. And then what kind is it? Propane, right? It's like propane gas. It's C3H8 because it's 2N plus 2. And then the very last one, 76. Yeah, sure. You should do one of them. Sorry, I didn't even notice that. Well, yep, it is what it is. The very last one would definitely be what, guys? Everybody? Decon. There's only one thing that can happen. All right, so finish whichever one you're on right there, and then we're going to take a couple notes from last week because we didn't. And it's on your printed notes from a while ago. It looks like this. Something that looks like this. I'm going to get it. Looks like this.
No.
There you go, working on the upper right corner. I only have 3 left, so I do really hope you got this.
I know exactly where it is. It was on my bed. It was on my bed. I remember I was like, this day, or we're done with that dude. So I would bring this. I'll just fill it out and then erase it.
Okay, guys, let's go. Let's go. The very first, in the upper right-hand quadrant, you'll see it says, the driving forces lecture notes, nothing reacts, or energy supply. So that's what we're starting on. This won't take more than about 15 or 20 minutes, but this is something I want to talk about before we jump into more stuff. Got one left. Matt, kindly pass it up. I swear, people. Swear on. If you don't have this, then jot down some. I mean, if you don't have the printout, then jot down something and you can write it down later, or erase it and give me paper back, whatever you need to do. Okay. So there are 2 driving forces in reactions. What do I mean by driving forces? I mean something that's going to make that reaction happen. There's got to be a reason something happens, right? Like there has to be something about the chemistry of it that makes the reaction happen. Because, like, if there were not reasons for reactions to happen, everything would be reacting. This lion and deer, they would just be reacting, right? Well, there's obviously a reason why they're not. It's because their chemistry, their molecules don't want to get together. There's no favorability in the reaction. Usually, 2 things have to happen. One, the reaction has to go to disorder, right? Disorder just means really unordered. So in your room, think about your room. Maybe you had some time to clean it, but how long do you think it'll take before it's kind of disordered?
Next day.
Very quickly, right? It takes a lot of work and a lot of effort to make everything put back in its place, fold everything, get your summer clothes back in, or get your winter clothes out, put your summer clothes in. It takes a lot of energy to do that. That's just not favorable in chemistry. We'd rather just let stuff hit the fan and just go with it, okay? Because in chemistry, it's just easier to allow disorder to happen and to put everything back in its nice and tight little, compact spaces. So we call that disorder. Another thing that happens really easily is releasing heat. It's really, really easy for things to get together and just make heat. Things get warm all the time. So we're going to talk about those 2 terms. They're called entropy and enthalpy in just a second. But I really want to take that first so you understood this part. What can happen when chemicals are mixed? Literally nothing. Which how do we recognize that in our types of reactions from last week? We write. What do we write, Matt? We write NR for no reaction. Now, what would cause a no reaction? Okay, so we're talking about activity series. So I'm going to say a less active metal is the single one, right? Is the single one because it's not going to replace, so then we say no reaction, which makes sense because sometimes things are just not able to react because they're less reactive. This is NR, by the way. And then the other one would be all spectator ions. And why would something have all spectator ions? Basically, there's no precipitate. There's no solid forming, so then if we cancel out all the spectator ions, it looks like nothing happened because literally they're just all chilling in the container together, not doing anything. So that's sometimes what happens, and we've actually encountered that. Another thing is that things react, just like all of our types of reactions, things react. And I'm not going to write down all of those, but they show an evidence of chemical change. And we can tell gas evolution, light production, heat production, precipitate formation, unexpected color change. We can tell something reacted because we can see a change. Now, sometimes you got to get a little off, right? Okay, so I'm making some brownies, right? Get the brownie mix, put the eggs, and applesauce, because it's better for you than oil. Chocolate chips, and you put it in a bowl and you put it in the pan. Is it going to bake on the counter? That would be awesome. But no, it's not. What do I have to do? All right, so that's me putting some energy into the process. Because it's not going to happen by itself. You got to give it a little oomph. There's something called activation energy. Who's ever heard of that? maybe in biology with enzymes. Okay, so that energy that we're applying is called activation energy. Guess what it does, guys? Activates the reaction. That's it. Okay, so reacts after energy is applied, meaning it's called activation energy. Is what that energy is called. And it's going to be labeled EA. Level sub A is just saying activation energy, and E is the energy. So after a reaction has been given a little to get started, maybe it's a spark, like a spark plug in an engine. That spark is going to make the reaction start, but it's not going to happen without that. So that's the 3 different types of things we can see in a reaction. Okay, so let's look at these 2 forces of reaction. This is what I was trying to talk about earlier. The 2 forces of reaction that can make a reaction happen are these 2. Entropy, and you should know that entropy is labeled as delta S. Delta is like and so if the entropy amount is favorable, meaning the reaction's happy with that, then we say the entropy is driving the reaction. Well, what does that mean? We think that reactions like to go to disorder because it's just not as stressful. Like, it's stressful to make everything very, very organized, be OCD all the time, right? It's kind of easy, just let things go. I'm not advising you to do that, but I'm just telling you that's how chemistry, that's how the chemical reactions work. So whenever you allow for the reaction to go to disorder, if you increase in disorder, we call that an increase in entropy. And an increase in entropy is great. It's very, very favorable. So an increase in entropy favors a reaction occurring, meaning it's going to happen. It will react. Will react. Rxn is reaction, so Rx is react. Okay. So the other driving force is talking about like energy in terms of temperature changes. This one is just energy changes in terms of arrangement of particles. This is energy change in terms of energy of like usually thermal energy. And it talks about potential energy a little bit, but we're really focusing on the kinetic energy. Ke is kinetic energy, and kinetic energy is directly related to temperature changes. So it's going to be talking about increase in temperature. So an exothermic reaction favors reactions, or process favors reactions occurring. And so when I say something's exothermic, do you think energy or heat is being released or absorbed into reaction? Released. You guys know exo means outside. And so if we're talking about energy, it's going to be going to the outside, which would be released. So this means energy or heat is released from the reaction. So if energy is being released, do you think delta H is going up or delta H is going down? Do you think delta H is increasing or delta H is decreasing? It's decreasing, right? So a correlation of exothermic, heat's being released, delta H is decreasing, delta H is representing enthalpy. Think of the thol as like thermal, enthalpy is related to like the thermal component, and entropy is related to the disorder. These 3 things correlate to each other. Exothermic, heat released, delta H is decreasing, going down. So what you need to know and basically memorize or understand or appreciate is that for a reaction to happen, 2 things have to occur. Should occur. The entropy should increase. So increasing entropy is a good thing, and decreasing enthalpy is a good thing. And if we can get happy, it's going to both of those reactions parts are favorable. The reaction will definitely happen. Sometimes one's going to be increasing and the other one's going to be increasing, or vice versa, decreasing, meaning one of these happy phases are satisfied. And we call that sometimes reacts because it's going to depend on some other conditions of the reaction. So did I put this table on your little notes? Something like this? Okay. So let's talk about if it's going to happen or not. And so what I meant by this very beginning stuff up here, when I said nothing happens, like literally nothing happens, okay? No reaction. If I say reacts and I don't have any conditions present, that means it reacts spontaneously. What does spontaneous mean? What if you were just like, you know, she just spontaneously went and did this? What does that mean? She did it without thinking. She just did it. It just happened. There was no reason for it. It just happened. There's no instigation. There's no push to make it happen. It just happens. So this means spontaneous. Spontaneous in chemistry means to react without intervention. Meaning there's no prompt to make it happen. There's no spark. There's no energy applied whatsoever, right? So reacting, which means to react spontaneously. Reacting with energy applied means to react non-spontaneously, but you can make it happen. So that's where the term spontaneous is going to come in here in just a second. Okay, back here. So if you can get an exothermic reaction, is that good or bad? Do we want that or do we not want that? We want it. We want a delta H to be negative. We want the delta H to go down. That's basically what that means. A negative delta H is delta H decreasing, going down. That's good. If the entropy, which is the amount of disorder, goes up, we call that a positive delta S, so it's getting more disordered. That's also a good thing. If it's like, yeah, then it is definitely going to happen. Yes, definitely going to happen. It's favorable, however you want to say it. Spontaneous, it's favorable. It's definitely going to happen. So you can probably imagine that if those conditions, those two factors were not satisfied, the reaction would happen. And that's what the second row is showing. If the delta H is positive, meaning it's going up, is that happy face or sad face? Sad face. Okay, we do not want it to go up. We want to release the energy to the universe. And the second option here with entropy, if it's getting less disorderly, what's another way of saying that? More ordered. It takes a lot of energy to do that. That's just not favorable for reaction. So that's a delta S that's negative, because it's negative, getting more ordered, less disordered. That's going down, so that's another sad phase. So this is a never. It will never happen, no matter what, because neither of these two factors are satisfied. So then we get into the ones where we have one satisfied, the other one not. So you can imagine, it's not always, but it's not never. It's going to be called sometimes, right? Kind of makes sense. So negative, does that mean endo or exothermic? Say again? Negative delta H? Exothermic, right. And exothermic, that's Cyclops there, okay? Negative delta S is what? Tell me the term that goes along with negative delta S. More disordered or less disordered? Less disordered. Not so great, right? We don't want less disorder. We want more disorder. We want craziness in reactions because it makes everything more stable and less like pent up energy. So that's good. That's bad. So we're going to call that sometimes spontaneous. So that's because they don't agree. And then the same case on the opposite terms here. Positive is endothermic reaction. That means that delta H is positive. Going up, it's getting colder. Really is what's happening there. And that's not good. We don't like that. And then the positive delta S is, would that be more disordered or less disordered? More disordered. So that's more disorder, which is a positive delta S, and that's a good thing. And so because they don't agree, we are happy and sad, it's still going to be considered sometimes. So positive delta S means what again? Positive delta S. More disordered. Positive delta H. Hold on, positive delta H. Endothermic. Negative delta H. Exothermic. Negative delta S. Less disorder or more order, right? So I always think of in terms of disorder because that's like literally the definition of delta S is the amount of disorder. Okay, so let's look at the reactions themselves and let's show how we can actually interpret which of the driving forces are favorable here. So if you're looking at the very first one, you see this kilojoule thing here, right? You know that energy is expressed in joules. We've talked about joules before. Cracking unit 1. But if energy is on the product side, it's being produced, right? Energy is being produced on the product side. Do you think that would be considered an exothermic reaction where the heat's able to exit? Or do you think energy is being put into the reactants to get started? Okay, so I'm hearing released because they're being released as products. And a released amount of energy is called delta H of what? Negative or positive? Negative, right, because that's exothermic. Okay, so we know one condition is exothermic. Is that good or bad? Good. So put a happy face. I think the happy faces help. I know it's childish, but it really does help. So that's good. Now let's look at the differences in disorder. So if we're talking about disorder, really the only thing we can look at are states of matter. What is the most ordered state of matter? A solid. Look how cute it is. It's like neat and organized. Great. Okay, liquid's kind of like wavy. It's a little bit more disordered. And gas is bouncing off the wall, hitting you in the face. It's everywhere. Right? So it's totally 100% disorganized or disordered. So if we look here, is this balanced? Yeah, okay. We have solid, aqueous, and aqueous is kind of disordered as well. Solid and aqueous. We can't really tell if disorder is increasing or decreasing because it looks the same. We have one solid on this side, we have one solid on this side. We have one aqueous and we have one aqueous. So now we would say that we cannot tell delta S change. So we would just say that for this reaction, the enthalpy is driving the reaction. It's making it go. It's like favorable on that condition, so it's forcing the reaction to occur. Because you can't tell the delta S. Okay, looking at the next one. If you told me the energy on the product side was exothermic, what do you think energy on the reactant side is? Endothermic. Can't you tell the energy is going into? It's like going into this reaction on the reactant side. So that's a delta H of what? Positive or negative? Positive. That's endothermic. Right. So that's endo. Is that good or bad? Bad. Sub-base. Okay. So now let's look at the states of matter to see if we can figure out the entropy. Aha. We see differences. We see solid liquid water, or solid water, ice, going to liquid water. So remember, as you go from solid to liquid to gas, you get more disorder. Positive, okay? So is that going to be a positive delta S or a negative delta S for that part? Positive, because going from solid to liquid, it's getting more disordered. That's great. So I'm going to erase this part some space. So delta S is getting more disordered. Yay! Okay, so who's driving this reaction? Who's making it happen? Entropy is making it happen because it's making it more disordered. Enthalpy is holding it back, but it's still spontaneous as it's noted above, so it's definitely fine. All right, let's do one more like this. Let's do one with all gases. I need to show you how you determine it from gases. So what's the delta H here? For this one with the N2H2 H3. So it's exothermic because the energy is on the product side. Good. And then is that happy or bad? Or is that good or bad? Good. Okay. And then delta S here. We need to balance this real fast. What do I need to do?
Putting 2 in front of each. Oh,
I'm on this one, sorry. So 2 in front of the ammonia. 3 in front of the hydrogen gas. Okay. So how many moles of gas on the reactant side? I want you to literally count up the coefficients. So how many are here? 1. How many are here? 3. So total 4 moles. So that's 4 moles of gas. 4 moles. That's a pretty good amount. On this side, we only have how many? 2 moles of gas because there's just a 2 there. So that's going to show you go from 4 crazy moles of gas down to just 2 crazy moles of gas. So would you say that's an increase in disorder or a decrease in disorder? Make a choice. Say it loud and proud. Decrease. You're going from 4 to 2. It's decreasing in disorder because there's just less gas. So decrease in disorder is a negative value. So that's a decrease, and that's a bad thing. We want increased disorder. So we would say in this case, the enthalpy is driving the reaction, not the entropy, because it's not a favorable condition. Okay, does this make a little bit of sense? Try the bottom 2 for me. This one and this one. Okay, so I think we all probably are good with seeing the energy on the left or right and recognizing as endo-exo. On this mercury oxide one, would you guys say the disorder is increasing or decreasing? Increasing, right. We have solid, which goes to crazy gas and some liquid, right? So it's definitely increasing disorder. So that delta S is what? Positive, because increasing is positive, right? And that's a good thing because we do like disorder to happen in the reaction because it releases pent-up energy. And then the second one, we have aqueous. And can you imagine what this is? It's probably liquid, right? Okay. So this one's a little harder. But what I want you to notice is that we have two different aqueuses going to a single liquid. So we have two different things going into one. It's getting more ordered. So this is more ordered, and this is less ordered. So this is more disordered, I guess you could say. So that's going to decrease in entropy. So decrease in entropy is a negative value, and then that's bad. So then your two driving forces would be the exothermic part in this one, so the enthalpy in the bottom one, and the entropy in the top one. Okay, so do me a favor. You guys have I'm going to give you guys a couple more minutes to work on this. So I know we just briefly went over some of these. You guys will finish those. On the very bottom, you see some review, mole relationships. This is the paper that you're writing on your own. On the very bottom, you've got the 3 mole relationships represented. So I want you to just work with a partner on those. Write on a piece of paper because you probably don't have. I don't know. You might have from that. But just need for parts to use your 3-prong approach. What are the 3 mole relationships? The mole is here. The first one has a relationship with particles, and what's the connector? Avogadro's number, which is
6.0.
Okay, so 6.022 times 10 to the 23rd, 4 million units, atoms, or molecules. There's 3 different ways to say particles. All right, so then we have the one in the middle that's going from mole to 2 grams, right? The molar mass is the connector because it's just dependent upon the compound. Look at the math on the PR table, so others on your for you. And then from mole to volume or liters, right? And what's the connector there? 22.4 liters per mole. Right. Okay, so I think you guys are going to be fantastic at this. And tomorrow we'll be moving on to our more stoichiometry. But you guys can work on some of this right now if you want to with a partner. If not, this is due tomorrow. And then reading guide 12, do we have questions or can I just go ahead and pick that up? So I think you had enough time to look over some stuff over break. So pass up reading guide 12 while you guys work on that for a couple minutes. Just pass them over to the desk right here next to Peyton. The same math desk, but he just moved. Yeah. Have a buddy. Matt, just wait. Can you wait till you do? Right. Yeah. Oh, if you need some like just confidence boosters, I'll come pat you on the back. I can see your work. Okay. So I know it's rough to remember some of this. Specifically, look at the stoichiometry in the bottom, guys. I want to make sure you remember at least one of them. Start on number one in the bottom. Now you're going to good function. Evan's little quadrant, go grab your Chromebooks. And then you guys are next. I'm just going to get some Chromebooks down here. Miles area, guys, go grab your Chromebook. Chase's whole area. Alina, you guys go grab your Chromebook. Last area over here goes in 1 minute, I need your attention, okay? So get your Chromebook, get on my website, go from there.
That was fun. That was fun. Terrifying.
Okay, and open your laptop, get logged on. I'm going to walk through number 1 with you real fast because it goes through 2 of the important relationships. And then I'm going to go to experimental design because you guys can finish that worksheet for homework, okay? So first, you took your molecules, and molecules are a particle, so that means that you have to use Avogadro's number to get to a mole. So that's why I used Avogadro's number of molecules of carbon dioxide on the bottom of this fraction, because the molecules and molecules, don't forget, they have to cancel. And that gets you to 1 mole of carbon dioxide, but the question said grams, so mass, and carbon dioxide weighs C plus O plus O, which is 44 grams per 1 mole. And so the unit here has to go down here because they have to cancel. So it's like a really helpful guide to show you. Like molecules has to go down here because it has to cancel. Moles has to go down here because it's to cancel. And then it leaves me with just grams, and that's why I'm allowed to say 14.6 grams. You may have made a miscalculation if you didn't put parentheses in your denominator. And because I saw somebody with some weird like exponents or something like there. So just watch your calculations. You kind of remember some of this though? I'm just trying to bring it back, but not like reteach it because we got to move on. Okay, so looking at this. Experimental design. So when you get on my website, go down to the bottom of the documents. It says Mythbusters. I'm going to show you briefly right here, and then you're going to do your groups for about 15, 20 minutes. Your research brief, if you've not seen the comments yet, get on there with your partner today and make edits, okay? Because it's a cumulative grade. It's about 300 points total, so it's like 2 test grades. So because it's a long-term project, so I try to reward you for your efforts, and I try to give you chances to regain points if you just misunderstood some directions or something like that. So use this format, okay? Just download this template and edit on here. But you'll put your question, your hypothesis, and some of the lingo here may not apply to your question, but try to incorporate it. If it doesn't work, then just revise your hypothesis some. But if we increase the time studied, then our test grades will decrease. I don't know. Okay, so you can see how the lingo works there. Levels and trials. The trials definitely, you guys might say, I'm using, this percentage of this hydrogen peroxide, this percentage, and this percentage, and that can be, that can actually be the levels. And the trials might be, I'm doing 2 trials in each of those. So that sometimes mixes people up, but try your best to ask me questions because it's really going to be dependent upon your test that you're doing. List the IV, DV, control, constant variables, and I have 3 listed here, but you can keep on going. This is every variable that is constant for every single trial. This might be the same person used, the same type of detergent, the same type of material, the same temperature used for every trial, the same atmospheric pressure. Whatever you need to include. And then this is where you'll tell me what you need from me and who's providing what for your experiment. Because sometimes you guys might think I have like every chemical known to man, but I do not. So make sure we have everything you need to get your experiment started. If you need to use my facilities, like come during teal or come after school, you'll just have to make an appointment and we'll make sure it gets done because I kind of need to set up some stuff for you guys sometimes. And then the description, including a diagram or flow map. This is one the part everybody leaves out all the time. It's like 10 points. So diagram or flow map meaning it's like a diagram that I could look at and you would exactly represent your procedure in written form. So I could look at either and tell the exact same thing. So it's like just a flow chart to show you step by step how you would go on. And then a preliminary safety, of course, is important. The preliminary data chart on what you might think you need to collect. And you'll adjust them as you go because you might get in the middle of the experiment and go, we got to collect this. Or I think we should do another trial. So this is like probably 70% true what's going to happen for your experiment. You're going to have to tweak it some. But it's like kind of getting to go time. After I approve your experiment, you can start. Okay, so this is due Friday. Work with right now with your group. If you make it a Google form, you guys can edit tonight. Nicole, yeah, you can share it with me. So I can edit. You have like, I did it actually once before. I didn't share it with your apps one actually. Yeah, I remember. I didn't. Okay, I must say. We got. Like the Belgian. Oh wait, I used to. What are we changing? Hair tips are really changing. Real hair waves are really expensive and aren't applied on hair. So my mom. I think I read. Watch that video. I'm not reading reviews. Okay. Yeah, I just. I gotta pull up my spreadsheet. Do you remember what you sent me?